Let me know if it happens again. Thank you. Okay, so you're going to do the space simulation that takes f of n space. And you're going to simulate it in that f of n space. But the thing about space-bounded simulations, they can run forever within that same space bound. If you have linear space, you can still run forever in that linear and not consume more than that linear space. You can reuse and reuse and rehash and reuse that linear space and keep running forever and still do useful things. How many get that? But occasionally, if that simulation runs forever in linear space, it must repeat itself at some point. That state, that space must acquire the same values it did before. Which principle am I invoking to say that?
Having a number of characters, stack characters, and a number of permutations possible for that state.
Yeah, everything counts as a state. Everything in the tape and the state you're in the machine, and where the read-write head is pointing, and so on, that's all part of your state. So what I'm saying is, if the simulation or the computation never exits that space bound, if you only have a bounded amount of space, bounded by f, like a million bytes of storage, and the computation runs and runs and runs for a very, very long time, eventually that million bytes of storage will look like it did 50 centuries ago, even if it changed a lot in the meantime. How many see pigeonhole principle at work here? Yeah, now you're getting it. Any questions about that? Because the memory, the state, whether it's your read-write head position on the tape, the contents of the tape itself, which state you're in the finite control, all of that as your state, will eventually repeat, because there's only a finite number of different combinations of tape content, state that you're in, where your read-write head is pointing, and that's about it. And yeah, it's a very large number. It's exponential in the size of the space. If you have n bits in the space, you have 2 to the n different combinations of those n bits, but that's it, 2 to the n. N could be large, but 2 to the n is even larger, but they're both finite, is the point, and they're both bounded. Okay? So if you only have a bounded amount of space, there's only so many state changes you can do before you repeat yourself. And if you repeat yourself once, and you are deterministic, the D there stands for deterministic, you will repeat yourself again and again and again in exactly the same way, like Bill Murray in Groundhog Day. How many have seen that movie? Okay, good. So you know what I'm talking about. Right? That's what determinism is. You're stuck in this loop now, repeating yourself over and over and over again. And if you're the simulator, you can detect that. Keep track of all the states that what you're simulating has ever been in. When it goes to a new state, see if it's any of the states it's been in before. And if it is, what should you do as a simulator? Take a wild guess. What does the simulator know about what it is it's simulating if what it is it's simulating has repeated a state and it's deterministic? What very critical piece of information do you now have? Should you keep simulating? Is there a hope this thing will ever end or halt? I mean, say, this thing may one day halt that you're simulating. I mean, say, for sure it won't halt. Good. So as a simulator, you can just stop and say, this thing will run forever. And you now are halting. And you can stop the simulation with the knowledge that for sure this thing will run forever, and you can report that. And the simulation now is done. So in a finite amount of space, in a bound amount of space, there's no need to run forever, even if you try. Because if you ever repeat yourself, you might as well stop and say, I will run forever, but I will stop instead, with the same effect. And you can thereby solve the halting problem for bounded space. So this is a variation of the halting problem. We only have a finite amount of space, a bounded amount of space. The halting problem is relatively easy to solve now. Keep running and running and running. If it ever stops on its own accord, fine, then you're done, and that's your answer. But if it doesn't stop on its own accord, and you ran for long enough, You can then again stop and say this will run forever. Either way, you're solving the halting problem correctly for bounded space computations. How many get that? And how long do you have to wait before you know for sure? Take a wild guess. Yeah, exponential amount, right? And the exponent depends on, this branching factor of, whatever. In this case, it could depend on the alphabet, how many characters you have, whatever. But it's no more than an exponential number of states that you can possibly be in if you have a certain amount of, storage to begin with. It's bounded, right? You can't be in too many different states, no matter how much time you have, because eventually you'll cycle upon yourself. And the simulator can detect that cycle by simply storing a long list of all the states that you were ever in. Just brute force. Every time you change a state, you do something more, see if you've been there before. It's tedious, it's long, it takes a lot of storage. That's why the exponent's here. So we just proved this theorem, that they can simulate a deterministic space computation of size f in, at most, an exponential amount of time, but no more. That's why you have this theorem here. These theorems will get more and more subtle and complex. Yeah?
So, if you're going to use this on like a computer, like a Dell computer, what resource bound would be sufficient for this to actually be useful to solve all the problem? How much space would you need to allocate?
Yeah, so I'm not suggesting that this is the best way to solve a bounded space halting problem. Because, in certain cases, there's other shortcuts that you may want to take. For example, if your code doesn't have any loops in it, just has assignment statements and case statements and if statements, and even if it has loops, but the loops have finite bounds, constant, hardwired bounds, not bounds of variable length. Then you can have some sort of an analyzer and look at this program and say, okay, because everything is bounded, all the loops are bounded, I'm only using if statements, there's no go-tos, there's no recursion, therefore it'll halt and everything. You can predict that and maybe you have a shortcut. So you don't necessarily have to do something that complicated. This is like the worst case that can happen. It'll never be worse than that. And in practice, sometimes better. Right? Any other questions or thoughts? Yeah.
So are you saying that the worst case of you coming back and seeing a repeated state is exponential time?
Yes. Yeah, because if it was any more than that, some state must be repeated by the pigeonhole principle. So it's very important here to understand the pigeonhole principle is like the linchpin of this theorem. Just like in the pumping lemma or the pumping theorem, some state had to be repeated. Here, some state had to be repeated too. Within that space, you can only have so many variations of what that space can contain, and eventually it will be repeated. And if it does, you can detect it. You're just using brute force. Yeah, that's what we're saying. Any other thoughts or questions? All right. So this one is not easy to prove. We're going to prove it probably. I don't know if we'll have enough time today, but certainly by next time. So Savage's theorem says that non-deterministic space F is contained in the deterministic space F squared. So if you want to get rid of your non-determinism in your space bound, you don't have to pay more than a quadratic penalty of what this says to make it deterministic. So this n becomes a d here, and the penalty is at most quadratic, the square of the original space bound. That's not obvious at all. That one's a deep theorem. And a corollary of that would be that deterministic polynomial space is the same as non-deterministic polynomial space, and that's why we just call it P space, not D space, not DP space, and NP space. We call it just P space because it'll be a corollary of this. In other words, all these polynomials will be contained in all these polynomials and vice versa. But this is the key to proving that, what we mentioned earlier again. Okay, so we'll punt on this one because it's hard. Okay, but that's the corollary here. Okay, now for particular polynomial space of particular exponents, it turns out that non-deterministic polynomial space n to the r is contained in the deterministic polynomial space n to the r plus epsilon for all exponents r and however small epsilon you'd like. This is not obvious either. We won't prove that one. This one we won't prove. But it's easier to prove than this one, I think. That means you can get rid of the non-determinism at low exponents of fixed size r if you only pay a little bit more, and then you end up with a deterministic computation, and you got rid of the non-determinism. So these are, in some sense, versions of the power set constructions for finite automata. How many can see that analog here? For finite automata, we had non-determinism also. But for finite automata, when we wanted to get rid of the non-determinism and make it deterministic, we did a power set construction, exponentiate the number of states in the worst case. And then we had a deterministic machine, a deterministic finite automata that accepts the same language as this non-deterministic counterpart from which we started. But we've gotten rid of the non-determinism and paid a potentially exponential penalty there too for finite automata. Here we're doing something similar, but now we're looking at space bounds and time bounds in general, not just states. Okay, so I hope all this makes sense. Any questions about any of this so far? So we didn't prove this one, we didn't prove that one. This we're saying is a corollary of that, but we did prove the first four. And of course, the book has much longer explanations with more words, and there's wiki pages on all these things, and you should be looking at all of that, not just listening to me here. This is subtle stuff. All right. Chomsky hierarchy reloaded. We've seen all these classes of languages, regular, context-free, and now we're seeing these for the first time. We see polynomial space right here, which is equal to deterministic and non-deterministic version are both the same. That would be a consequence of Savage's theorem, which we're about to prove. Exponential time with a finite exponential space. So you have more space. So space exponential time because you cannot use more space than you have time to use. So that's this containment here. It may or may not be proper, by the way. It's still an open question. So there's many open questions here, all up and down this hierarchy. There's P space, and there's NP and P. So their containment is like this because P is a subset of NP because determinism is a special case of non-determinism, or conversely, non-determinism is a generalization of determinism. That's why you have this containment here, P and NP in this Venn diagram. This whole thing is a Venn diagram. And now we've defined several other classes here, and there'll be more and more classes kind of piled up on this as we go along. Right now I'm keeping the picture simple, if you can call that simple. The real picture is I'll show you the real picture of all the named classes. Probably in a couple of lectures, there'll be hundreds of them. And that picture I won't even be able to draw myself, and the font will be really small, but just so you know, it's called the Complexity Zoo. It's on the web, actually. These are all live links to the actual classes, complexity classes, that you can get more information about them, but I digress. So there's P space. By the way, we don't even know if P space is equal to P. It may or may not be equal to P. P and P space may coincide. We don't know one way or the other. That's another open question. But if P is equal to P space, both are equal to NP, and P is equal to NP, and that's a corollary of potentially the possible case that P is equal to P space. P is equal to NP will be a corollary of that. So if you can prove that P is equal to P space, P is equal to NP will be a corollary, and then you'll get $1 million from the Clay Institute and probably a PhD on top of that, and probably head of engineering at Google as well, because everybody will be very impressed with you. Okay, any questions about these new classes? They were there all along, but now we defined them and we showed some relationships among them and containments and so on. Right, so P, NP, deterministic polynomial time, non-deterministic polynomial time, polynomial space, both deterministic and non-deterministic, exponential time and an exponential space. And by the way, all these are all decidable. Decidable means there's an algorithm for it. I don't care how long it takes, how much space or how much time it takes. Decidable means you can do it. With some algorithm, I don't care how slow. So you can see all these are within the decidable. So there's a lot of structure within the decidable languages or the decidable functions inside here. And there's a lot more structure that I'm showing you now, and we'll get more into that later. There's infinite hierarchies, actually, all up and down. In fact, all these time and space complexity classes are in each of these regions. There's an infinite number of complexity classes in between. Okay, we'll get to that. Any questions so far? Okay, so there's a lot of open questions. In fact, most non-trivial questions about these complexity classes have not been resolved. It's very hard to prove things in general, especially non-existence proofs, to show that there is nothing in that class that's not in the first class, and so on, like P is equal to NP. Okay, so let's talk about the complexity hierarchy. So it turns out, so you might think, okay, so we defined a lot of complexity classes in terms of time and space, right? There's linear time and quadratic time and cubic and quartic and quintic time, and then there's all polynomial time, and then there's exponential time, and then there's super exponential time. You can define all these classes. But that doesn't mean that they're all proper supersets of the lower classes. Maybe nothing requires more than exponential time. Maybe exponential time, because exponential time, even polynomial time, there's an infinite number of problems and languages that can be solved and recognized in polynomial time. And they're all different from one another. Like, for example, all the regular languages can be done in linear time. Right? How many get that? All the regular languages are in linear time, right? To simulate the finite automata. And there's an infinite number of different regular languages. So maybe quadratic time is enough for all languages in the universe, all the other languages that are not even regular. And if not, maybe exponential time is enough. And there's nothing beyond that. Nothing that requires more than exponential time to compute. That may have been the case if we didn't think really hard about it. And we're able to prove that if you have more time, higher time bound, there are languages that can be done in the higher time bound and space bound that can't be done in the lower time bound or space bound respectively. So we're able to prove that if you have more time or space, you can compute new languages that could not compute before with less time or less space, which is amazing, actually. So it's an infinite hierarchy of time and space classes that get you more and more and more languages. And each one already contains an infinite number. But you already know that the infinite union of countably infinite sets is still can be countably infinite result, right? You know, I think that's one of the problems you have to prove on the homework, right? That the countable union of an infinite countable union of infinite countable sets, of sets each of which is infinitely countable, could union together to another countable set, this dovetailing, right? In fact, all the fractions have this property. The fractions were arranged in infinite number of rows in the plane, and then we dovetail through all of them, and it was still countable, right? So just because the infinite number of languages in any class doesn't mean that there are no more languages beyond that class. In fact, there's plenty. There's an infinite number at every level. So we're about to prove this theorem, actually. So this will start getting into deep water here. So what we're saying is that no time complexity class, or space complexity class for that matter, we'll prove that separately. It's a very similar proof. The proof is almost identical. Contains all the decidable languages. So the time hierarchy is infinite. There's infinite number of hierarchical levels to this time classes or time hierarchies, so-called time hierarchy. Same for space hierarchy. In fact, same for any resource hierarchy. It doesn't have to be space or time. It could be many other resources. Right? We talked about other resources like page faults, disk accesses, messages sent across the net, heat, power. There's the same theorems apply to all of those, just so you don't think it's just about space and time. It's very general. Okay, so that means there's decidable languages for which there's algorithms. This can be decided yes, no. With algorithms, always stop, but take larger and larger time to compute and larger amounts of space to compute for however large you can imagine. In other words, there's languages that require factorial time that cannot be done in polynomial time. And there's languages that cannot even be done in factorial time because they require factorial time. Right? Factorial is just, n factorial, take the result, and factorial that. That grows really fast. I mean, factorial already grows fast. And there's languages that can't even be done in that time or space, require more. We're about to prove this. How do you prove such a thing? Diagonalization. Remember, I told you you'll get a lot of mileage out of diagonalization. You've already seen many examples where diagonalization came in and saved the day. This is one more scenario. In fact, dovetailing will come in handy here too. Same comment about dovetailing. Very, very useful. You get a lot of mileage out of that too. Okay. So first, fix some lexicographic order for Turing machines. Machine 1, machine 2, machine... We already know how to do this. You can enumerate, you can count all the machines, right? Machines have finite descriptions. List the states, the transition function as a string, big string, but a string. And then arrange the strings by length and within lexicographic order. Number them all, and you got some canonical order, some lexicographic order on machines. So you can do the same thing for programs. List all the programs from small to large, number them all, and you got it. How many get that concept? Talked about it many times, right? Just reminding you. Okay, so then you can do the same for inputs. You can, think about the inputs as input 1, input 2, all the strings in sigma star, you can encode them as integers again, but this is just dovetailing. So we're just dovetailing here across machines, across inputs, you can just number them. So if I say machine number 17 with input number 34, you know what I'm talking about. It's the canonical ordering, the lexicographic ordering of the machines, and you take the 34th one, and we all know what the 34th program is, or Turing machine is, and same for inputs. Okay. So now we're going to define a weird language, and that language will be all the indices I, such that the ith machine, or Turing machine, doesn't accept the ith input within time t of I. So t of I is this bound that we're trying to show that there's things that require more than t of n time, right? That's what this t is. For any time-bound t of n, there exists a language that's A, decidable, and B, cannot be recognized or decided within any less time than that. In fact, requires more time than t of n. Okay, so that's what this t is here. It's this time-bound, supposedly, that's enough to recognize all decidable languages, but we'll see it's not enough. We need some more time than that for a particular language, and we're calling it L. It's that language, L. So L is decidable. How is it decidable? You can simulate it, right? Because we know where all the machines are. So an input I comes, so we pick the ith machine out of our lexicographic order. Then we simulate the ith machine on the input I, and we do that for a while, okay? In fact, we do that for t sub I time steps, or state changes, and then we can make this decision. We see if this machine, the ith machine, accepts or doesn't accept the ith input within time t of I, and we accept it even if we say it's in the language, we report or decide that it's in the language if and only if the ith Turing machine does not accept the ith input within time t of I. So t of I is just a time function. We can compute t of I, then start the clock, start counting the ticks. T is equal to t of I from 1 to 2 to 3 to 4 to 5 to up to t of I time steps, or state changes. Then start the simulation, and after t of I time steps, stop the simulation and see what the ith machine did on the input I, and then do the opposite. Right? So that's how L is defined. It's all I that the ith Turing machine does not accept I within time t of I. Okay. So we're being contrary. We're seeing what the simulation would do, and we do the opposite. You can sort of see where this is going. This is beginning to smell like the proof for the halting problem. How many can sort of see that? Okay, and sure enough, it is very similar to the proof for the halting problem that Turing came up with, that we proved, many weeks ago now. So the question is L within this deterministic time t of n bound? And the answer is no. We're about to prove this. So again, we just showed it's decidable by simulation, but it's not decidable within that time. Why? Because very quickly we arrive at a contradiction if we assume it's decidable within that time. And here's the contradiction coming up. So if it's decidable within that time, then there's got to be some Turing machine, call it M sub k, and k is its index. Every machine now has an index according to this lexicographic order. So it's the kth machine, let's say, decides this language L, because it is decidable. And we assume towards contradiction, it decides it within that time-bound t of n. Because this language L we define is decidable by simulation. We just showed how to simulate it. But the question is it simulatable within that time-bound? Okay, so if it is, then here's the decider M sub k that we just defined in purple, color-coded. that decides this language L. I comes in the door. What is I? I is just a string, or the integer corresponding to a string. Now it's equivalent numbers and strings because of this dovetailing business. Is that video still going on, by the way? Yeah, good. So I comes in the door, and basically you now, M sub k, you the decider for language L, see if M sub I accepts I within T of I steps, and if that's the case, if it does accept it, then you reject. If it doesn't accept it, then you accept. In other words, M sub k does the opposite of what Mi does on the string I. Okay. So that's the definition of what M sub k does. It decides, it decides L within, presumably within this time-bound T of n. So I'm just copying that machine here, so it's on this current slide, so we don't have to go back to the previous slide. So now, see what happens if you feed this M sub k its own index. In other words, you feed it to itself, just like the proof for the halting problem. So we're driving towards a contradiction here. Russell's paradox is beginning to loom here. Pinocchio is saying, my nose will not grow. Cantor is smirking, and here's what's happening. We feed k to itself here, k to this machine M sub k. Okay. Now, if k was an element of the language L, M sub k will decide that, accept, that's what it's supposed to do correctly, right? So it must accept k within T of k time, right? But if it does, then this will kick in, and it must then therefore reject. So if k is an element of L, M sub k must reject that index k, and therefore k is not an element of L, because this machine here, M sub k, accepts the language L. Okay. So the only thing that could save us now is the opposite. If k wasn't an element of L, this machine must reject, because it's always supposed to tell correctly if its input is an element of the language or not. And this part will say it's not in L, but if it's not in L, the else will kick in, and then it will accept. And therefore, it is in L. And either way, you get the opposite thing happening. So you have a contradiction here. You have something of the form P, if and only if not P, for some proposition P. And that's a contradiction. In this case, k is an element of L. So k is an element of L if and only if it's not, which means one of our assumptions was false. Okay. So what was our assumptions? We assumed a couple of things. We assumed that L is decidable, and we assumed that it's decidable within this time-bound T of n. And it is definitely decidable because you can simulate it and decide, and that's not hard to do. So the only false assumption was the other one that we made, namely that M sub k itself works in time T of n. And that's a contradiction. So we have here, in summary, a language that's decidable, but not within time T of n, which means T of n isn't the ultimate time bound that contains all the decidable languages, only some. And by some, I mean an infinite number, sure enough, but not all of them. There's still an infinite number that are not within this time class, the time of T of n. So we just showed a hierarchy, a time hierarchy. How many understand at least the result, not all the nuances necessarily of the proof? The result of what we showed, just a statement of what we showed. Okay, that's about half the class, 2/3. I'll take it, because this is subtle stuff. And you need to read about this in the book. You need to look at wiki page. You need to meditate over this deeply before it completely sinks in. Right? This is basically a regurgitation of Turing's proof of the halting problem being undecidable, except now we add the extra complexity of time bounds. We're watching the clock, the stopwatch, as we're doing this. Okay, so we're watching the clock here. That's why I have this icon going on, the clock, the stopwatch. We have a question? Yeah, so the general technique of feeding something to itself, it's basically diagonalization. Diagonalization, but not necessarily in a big, long table, although you could draw it as a table. In fact, I have a table version of this proof. Maybe that'll help shed light on it. So this is kind of an alternate way of looking at the proof. So I'll just show you the whole thing. right? So assume that all time-bounded, T of n time-bounded computations of Turing machines are along these rows. So here's the first time-bounded Turing machine, the second time-bounded Turing machine, this third time-bounded. When I say time-bounded, I mean time-bounded by T of n. T is some fixed function, like quadratic or cubic or exponential. And here's what each of these machines do for all these strings in sigma star. So here are all the strings in sigma star, A, B, A, B, BA, BB, and so on. They're listed, they're just numbered. And here's what each machine does on every string. That's what's happening, this big, long, infinite matrix. It's infinite to the right, it's infinite down. But it has a 0, 0 origin here. So it's like a one quadrant in the plane, if you will. But these accepts and rejects, accepts being green checks, rejects being red X's, these accepts and rejects are what these machines will do on all these strings. And by the way, each machine always halts on all of its inputs because it's a decider, because all these languages are decidable. And in fact, they're all run in time T of n. So now we're going to construct a new machine here that will do the opposite of what all these machines do down the diagonal. It's going to go down the diagonal, and this machine here on the first input, on the second input, it will do the opposite of what the second machine does on the second input. On the third input, it will do the opposite of what the third machine does on the third input, and so on down the diagonal. So what this machine will do on various inputs is different than what each and every one of these machines will do on at least one input, a diagonal input, and perhaps on other inputs as well. So that means this machine doesn't behave like any of these machines in this infinite table. How many get that? Just like in the halting problem proof, basically. We could have done it like that too, but now I'm actually showing you the diagonalization graphically rather than just talking about algebraically, right? But so there it is, the actual diagonalization. Right? So this language down here is decidable because to decide it, all you got to do is look at which input I you're being handed, figure out what the ith machine is. It's easy to do. And then simulate the ith machine on the ith input, and then do the opposite. And you'll be computing this function here, or simulating this machine here, but you can't do it within that time because these are all the time-bounded, T of n time-bounded Turing machines or computations. So it's computing a different function than all of them, which means that function is decidable, but it's not decidable within that time. In other words, it does something different than all these time-bounded functions, all these infinite number of functions that all work within that time-bound T of n. So that's an alternate way of looking at the proof of the last two slides. This time using a picture, a table, where you can actually see the diagonalization going on, as opposed to just saying it's algebraic and using words to define it. Here we kind of actually go down the diagonal. So that's kind of an alternate way of thinking about the last two slides. Any questions about this? Because now we're going to repeat the whole thing for space. The good news is it's almost identical to time. The proofs were very similar for space. Yeah. Countable. Why? Because the total number of Turing machines is already countable. Unbounded machines. Why is the total number of Turing machines countable and not uncountable? I can ask the same thing about programs. Why is the total number of programs of any kind you want in C or C# or C++, why is it countable and not uncountable? Up there, yeah. Sort all the machines by their description. The descriptions are all finite strings. Sort the strings by size and size lexicographic. Any given size, and most of them are not even Turing machines. Some of them are Shakespeare's Hamlet or some other thing. Right? So those are bounded by a certain time or space. Yeah, there's only a subset of that. And if you have a subset of a countable set, it's not going to be bigger than the set itself. It's not going to become uncountable all of a sudden if you just take a subset of it. Yeah, good question. Okay. So we see the power of lexicographic ordering and of diagonalization and of dovetailing over and over again. Right? The same three techniques used again and again. That's why we harped on them so much the first few weeks of class. right? Because if you had to worry about the proof and separately worry about what is diagonalization and what is dovetailing and what is graphic order, at the same time, that's just too much. So we tried to nail down those concepts first really hard, the first homework and the first couple of weeks of class and extra credit problems, and then now we can use them, hopefully, with some agility and grace to prove much deeper things, like this one, okay, that we just did. Any questions or comments so far? All right, here's the same story for space, and it really is the same story. So if you have any space bound, there exist languages that cannot be done within that space bound. Same for time. So you just proved it for time. We're about to prove it for space. Very similar proof. A couple of minor differences, that's all. So we're saying that no space complexity class contains all the decidable languages. There are languages that require longer and longer amounts of, bigger and bigger amounts of space to compute. Okay. And again, it's diagonalization. The proof is almost identical. We use lexicographic ordering for all the machines, same as we did before in the previous proof. And you can interpret, the inputs as, again, integers or strings arbitrary, alternatively, because dovetail through all the strings in sigma star and number them, same as before. And we'll define a language very similar to before. L is the language of all strings or integers, but it's really strings, such that it contains I if and only if M sub I does not accept I within that space bound S of n that we're trying to show is not the upper bound for deciding all decidable languages. So L is decidable. We can decide, so if you get, how do you decide L? You get I give you I, how do you decide whether it's in or not? Well, you go to the lexicographic ordering and figure out what M sub I is, the ith Turing machine or the ith piece of code, the ith program, and then simulate it on I for S of n space, using S of n space only, no more space than that, and accept if and only if the ith Turing machine does not accept I within S of I time steps, and because the space is bounded, you will know what it does after a while and then can do the opposite. So we define it very similar to before. The only hitch here is what about infinite loops? In time, there's not unbounded time. If you have a time bound and you try to exceed it, that's easily detectable, right? So we kind of went through this argument half an hour ago. You try to exceed your time bound, I will know by holding a stopwatch, and when your time is up, I will say, okay, you're done. Like you're taking an exam, pencils down, your time is up. But if I put a space bound on computation, you can compute within that space bound and reuse and rehash that space for arbitrary amounts of time. So how do I know you've done the same trick as half an hour ago? If you repeat your state after a while, then I will know by keeping track of all your states. Right? Because if you have only a bound amount of space, if you only have 1 million bits to work with, and you keep churning and churning and computing for Google years, eventually that state will repeat by the pigeonhole principle. And then I can detect it, and then I will know you run forever, and then I can stop you and say, okay, forever, you know what you're going to do. And then the simulation is over. I will not have to run forever with you to see what you'll do. That's the space. How many get that? So we went through this half an hour ago. Same situation here. So that's what I mean by infinite loops are now detectable within a bounded space. So if the space is sharply bounded, you can detect infinite loops within that. Okay. So it is decidable. Okay. But is it decidable within that amount of space? And the answer is no. And that proof is very similar to that before. So the word's contradiction assume that there's some machine M sub k that decides this language L, right? And then if it does, you have the same contradiction as before. I'll just breeze through it because it's very similar to what we had before. Right? If you feed its own index to itself, and that index is in language if and only if it's not in a language, it's a contradiction. And the only two assumptions we made is that it's decidable, and it's not even an assumption because we proved it. So for sure it's decidable by simulation. but we assumed it's simulatable within that space bound S of n, and it's not. So it's decidable, but not within that space. So now we show that infinite hierarchy in time and infinite hierarchy in space, because these functions get larger and larger and larger. If you don't believe me, if you have the function f of n, 2 to the f of n is always larger than f of n asymptotically, and there's many things in between even. So you can always get more and more new languages you couldn't recognize before. They get arbitrarily hard to recognize in terms of space and in terms of time, in fact, in terms of both. And of course, at the very upper limit, there's languages that cannot be recognized in any space or any time, however large. Give me an example of that. 3 seconds, go. Take a wild guess. Sure. I said, we just proved that some languages take arbitrary amounts of space to decide, arbitrarily large. Not polynomial and not even exponential, maybe super exponential or factorial time and space. So for every space bound, there are languages that are still decidable, but they require more than that space or more than that time, and we just proved that. We proved the infinite hierarchy going up in space and time requirements for certain languages or functions to compute. So then my question was, there's languages that are even outside this hierarchy. They require so much space and so much time that no fixed amount of space, however large, will suffice. There are languages that cannot be decided within any amount of space or any amount of time, however large. Like what? No, alphabets are finite. He's asking about infinite alphabet. No dirty tricks here. So give me a function that's well defined, it exists, but cannot be computed using polynomial space or time, exponential space or time, factorial space or time, super exponential space or time, or any other space or time bound that you care to put. The whole thing problem. So it wasn't a hard question. I just wanted you to make that connection. Okay. So we already saw things that are so hard that no amount of space or time will suffice to compute them. And now we're seeing a lot of things that can be done that are in between the trivial and this impossible type halting problem or worse. Okay, so now we're starting to split hairs here. And things are getting more complicated because we're doing this. And of course, you draw the same kind of table for this space hierarchy and go down the diagonal, same argument as before. So these two proofs are almost identical. They're both rely on diagonalization and dovetailing, and of course, canonical ordering of Turing machines and equivalently of codes, right? And next will be Savage's theorem. What I promised to you would be non-trivial. So if you think everything now is abstract, wait till you see this one. Wait till you get a load of this. Okay, so luckily we're at the end of the lecture almost, so this will be mostly next time, but I'll give you a preview. Basically, we're going to show that non-deterministic space can be simulated in a deterministic space with only a quadratic penalty. Not exponential like the others, but quadratic. You at most have to exponentiate the space if you want to jettison your non-determinism and do away with it for space bounds. This one will be subtle. Okay, any questions about anything? So we've taken the midterm. How many are happy with their midterm performance with the questions? You've seen them before, right? They came straight for the homeworks. Okay, any thoughts or comments about the midterm? We're busy grading it now, of course. It takes a while. There's a couple of hundred of you, but we'll get it to you as soon as we can. Question? Okay. And the fourth homework is out. How many have started working on the fourth homework? Good. I see some hands. It's not too late. So it's not too early. You should solve as many of as you can. This homework is more subtle, right? Because we're getting into deeper theoretical waters here. So please work on it early, work in groups, come to the TA's problem-solving sessions, and we'll see you then. over and shut that video off and bring the whole tripod down here? Just press the off button.